So this week we'll be learning a new lab technique called calorimetry. In the previous videos you learned a little bit about enthalpies of reaction, Hess's law, and the different types of calorimetry. I'm going to sum up a little bit here and kind of give you a little introduction to the problem. So whenever you are breaking and making bonds, energy is involved. So when a chemical bond is formed, energy is released to the surroundings because the electrostatic attractive force yields a negative potential energy. So some of you saw this in class, this FA18 simulation where you move the atoms relative to each other, and if you're at long distances, that electrostatic interaction is minimal. As you get closer, that electrostatic interaction increases, but it's an attractive force, so you increase the magnitude of that force, but it becomes negative, okay, because they're attracted to each other. When you break a bond, you require energy to pull them apart. So because these two atoms are attracted to each other, you have to put energy in order to pull them apart. So that manifests in Coulomb's law here, where the charges on the two atoms, maybe this is a nuclei of one atom and an electron of another atom. If they are attracted to each other, then you have a plus charge and a minus charge that are attracted to each other, and you have to put energy in to pull them apart. So when a chemical bond is formed, energy is released. When a chemical bond is broken, energy is required. Now, I do understand that some of you who are in biology right now may have remembered a different rule for this, and I'm hoping I'm going to address that today as well. So if you recall from the beginning of the semester, we said that there was evidence of a chemical change would be in the form of heat. A couple weeks ago, we did an acid-base reaction between HCl and NaOH. And if we did our net ionic reaction, we canceled everything that was the same on both sides, and we got this reaction where we're actually adding hydrogen ions plus hydroxide ions to make liquid water. That reaction is forming a chemical bond. We're creating a chemical bond within hydrogen, and that actually has a heat of reaction or an enthalpy of reaction where energy is released to the surroundings. So because we're making new chemical bond here, energy is released to the surroundings as heat. Now this heat should heat up the solution, and maybe when we did titration you would not have noticed because we did it slowly enough that that heat was dissipated. In the case of calorimetry, we would dump these two together in a short amount of time, and it would release a significant amount of heat, raising the temperature by about 10 degrees Celsius, so that's pretty significant. Often you'll see this reaction given in an energy diagram then, where the reactants are given on a line at their enthalpy, at their standard enthalpy, and the products are given on another line at their standard enthalpy. And which direction reactants to products you go, right, determines the enthalpy of reaction. So in this case, the products are at a lower enthalpy, standard enthalpy, than the reactants are. And so when you create that bond, you go from a high energy state to a low energy state, and energy is released. So we have that minus 57 kilojoules per mole. One of the reactions we'll be using here involves some solids that we have to dissolve. So we have to break some bonds, and then we also have to make a new bond. So calcium carbonate, we're going to precipitate out of solution, and to make a new bond. So we have some amount of energy. So here's my reactants, right? I have to break some bonds in order to dissolve them into water, into their ions. And then I'm going to make new bonds to create my calcium carbonate. And if my final product is lower in energy than my initial reactants, then I'll have a heat of reaction that's negative, just like the making water example in the previous slide. This is called an exothermic reaction. So heat is released. This energy from the system is actually released into the surroundings, and we'll get the water or whatever this solvent is in is going to heat up, okay? But maybe it takes more energy to break my bonds than it does to make my bonds. So if I require more energy to break the bonds, than I get back when I make new bonds, then overall, from my initial state to my final state, I will have an increase in energy. And in that case, the heat of reaction, or the enthalpy of reaction, will be a positive value, and that we call endothermic. So in biology, when you may have learned that making bonds, like making sugars from carbon dioxide and water, requires energy, it's just that it takes more energy to break the bonds in water and carbon dioxide than you get back when you make the sugar. Okay, so that's a net reaction effect. And then you may have learned in biology that when you burn the sugar to get energy out, okay, that breaking bonds will release energy. But what's happening in that case is that it takes less energy to break the bonds in the sugar than you get back when you make new bonds in the water and carbon dioxide. So again, that's a net effect. In general, always, if you break a single chemical bond, it will require energy. And if you make a chemical bond, it will release energy. So what you've learned in biology is not incorrect or inconsistent with this. It's just that what you learned in biology is a net effect. You're looking at this delta H of reaction, not an individual step of breaking and making bonds. In the previous video, you will have learned a little bit about Hess's law, that if I want to measure the delta H of this reaction, I can also measure or think about the sum of these two steps, right? I can break bonds, and that's going to take some energy. I can make bonds, and that's going to release some energy. And if I sum those two steps together, then I will end up with my delta H of reaction. So Hess's law says that we can just sum up all those steps to get the reaction that we're interested in, the enthalpy of the reaction that we're interested in. So we have the enthalpy of dissolving. That's going to be a positive value because it's going to require energy that we put in to break bonds. And then we have the enthalpy of precipitation, or making those new bonds, and that's going to be a negative value. So the enthalpy of reaction is the sum of those two things, a positive value and a negative value. And if the positive value outweighs the negative value, then you'll have an endothermic reaction. If the negative value outweighs the positive value, then you'll have an exothermic reaction. So in lab this week, we have three reactions that we can measure. We can dissolve calcium nitrate into water to make ions. We can dissolve sodium carbonate into water to make ions, and we could mix sodium carbonate and calcium nitrate, dissolve them, and create the calcium carbonate precipitate. Okay, our goal here is to measure the enthalpy of dissolving for calcium carbonate. But calcium carbonate is an insoluble salt. So if we just throw calcium carbonate into water, it's not going to dissolve. So we can't measure it directly. So instead, we're going to do these three steps that we can measure directly. We're going to use Hess's law to manipulate these equations and add them up together so that we can predict the heat of dissolving for calcium carbonate. How are we going to do this? Okay, we're going to use a coffee cup calorimeter. So in the previous video, he explained really well what the coffee cup calorimeter does. We're at a constant pressure, so we've got a constant pressure system. Our system is going to be dissolved in water, so we're going to have some water in the cup. We're going to throw some solid salt in there. We're going to mix it up, and we're going to measure the temperature rise. We're using styrofoam because we want the heat that is provided by the reaction, that dissolving reaction, to be contained in this water. We don't want heat from outside the room to get into that water, or vice versa. And so we use a good insulator here. You maybe use a double stacked coffee cup to keep that system adiabatic. So adiabatic means there's no exchange of heat between what you're measuring and the outside universe. Okay. So what we're going to see again is a change in temperature, and you could do this with a traditional thermometer. We're going to be using a vernier temp probe, so we'll collect temperature in time, and then we're going to throw some salt in there, and the temperature is going to change. Okay, and hopefully we don't get drift like you see here in this plot. Hopefully it'll just level out to a constant temperature, and then it'll be really straightforward to measure the difference between the final temperature and the initial temperature. Once we have that change in temperature, we need to think about how do we get the enthalpy of reaction from that. So the enthalpy of reaction, the change in the enthalpy for your system, is equal to the heat that's exchanged with the surroundings. So if we measure the temperature rise of the water in the calorimeter itself, then we can understand how that responds to heat, and we can account for that and calculate our enthalpy. So the heat that is required by the reaction, so say we have an endothermic reaction, the heat that's required by the reaction will be equal to the heat provided by the surroundings. So this is the same magnitude of number. You'll notice that there's just a negative sign here, right? Which says if this is required, then this is endothermic, this is a plus value. The same amount of energy must be provided by the surroundings, and then that means it's exothermic for the surroundings. An easier way to think about this is the opposite. If I have heat produced by the reaction, then there's going to be the heat absorbed by the surroundings. So if this is a negative value because it's produced by the reaction, then this is going to end up being a positive value because it's absorbed by the surroundings. Now the surroundings in our case are made up of two primary parts. We have the calorimeter, so the heat absorbed by the surroundings is broken into the heat absorbed by the calorimeter and the heat absorbed by the water. We can characterize the heat absorbed or relate the heat absorbed to a temperature change using Q equals mc delta T. So here is the mass of the substance, the heat capacity of the substance, and the change in temperature. In this case, the heat capacity is given by joules per gram degree C. Or we might just have the heat capacity times the delta T. In this case, the units would be joules divided by degrees C. So if we use this expression and replace that for calorimeter and water, then we're going to get a calorimeter constant. What's the heat capacity of the calorimeter itself? And then there's the change in temperature that we're going to measure. We have the mass of the water that's present, the heat capacity of the water, and the change in temperature of the water. Now these two delta T values are going to be the same. It's the same value that we're going to measure. And we can measure delta T again by looking at T final minus T initial. The heat capacity of water is given as 4.184 joules per gram degree Celsius. So we know this value, we know this value, we're going to measure delta T, and we want to find Q of reaction. So we need to calibrate our calorimeter to determine the heat capacity of the calorimeter. In order to do that, we're going to use a reaction of known heat production. So for example, that acid-base reaction between HCl and NaOH provides a known amount of heat. If we know how much heat should be evolved from that reaction, then we can measure the change in temperature. When we do that reaction, we know the mass of water we're going to use. We know the heat capacity of water. That's a constant value. So then we can solve for the calorimeter constant. So in this first week of calorimetry in lab, this is what you'll be doing. You'll be verifying Hess's law for the reactions that we're going to run. You're going to predict what we should get out of our reaction based on Hess's law and some literature values. You're going to run the calibration measurements to determine the calorimeter constant. It should be a pretty small value. And then in week 2, you're going to use that calorimeter constant to measure the temperature change when you dissolve salts to calculate the heat of reaction.